This question is again taken from an exam, and it's not a difficult question. In fact, by if you have seen the four problems done till now and tried to solve them yourself, this is a pretty easy one. And in fact, when you keep practicing things, such problems are never difficult. However, if you are doing it for the first time, obviously you need to go to the problem one and start seeing the videos in a sequence. In this network, the question is in how much time the capacitor charges to 1 volt. So we are interested in the voltage of the capacitor. So let us take this as our response. But if you remember that in a series circuit, if we take the current as the response, that is more meaningful. Why? Because we have to encounter di by dt somewhere, and that requires the knowledge of this VL. So we can take this, but taking this would be more meaningful. And then once we know IC, we can find VC. What is the relationship between VC and IC? We know that the capacitor current is equal to C dVC by dt. So knowing this, we can know this by this expression. VC is equal to 1 over C integral 0 plus to t of IC plus the value of the capacitor voltage at 0 plus. So using this relationship, we can find that. We can start finding directly solving directly for VC. It's completely your choice. Somebody may choose to start directly solving for VC. Someone say, okay, I am going to solve for IC and then I am going to do this. Somebody may say, oh, taking this integration is not going to be easy, so I'm going to solve directly for VC. So let us see what we can do here. What is given is, for the circuit has been in a steady state for a long time, for t less than 0. So for t less than 0, we have ut here. So this would be a short circuit. So there would be no energy left in the circuit. Or now these are two conflicting things. So you see, sometimes you have to pay attention to the question as well. The system is assumed to be in steady state, operating for a long time for t less than 0. Now in t less than 0, this would be short out and there would be no energy left if the circuit has been operating for a long time. However, the values given say that VL0 minus is 2 volts. We have 2 volts here, and the current through this capacitor before t is equal to 0 is 3 amperes. While all other initial conditions are 0, how these initial conditions were obtained is not of concern. So we have two conflicting things here. Actually, this should not have been written here. In fact, instead of this, the question should just give the initial values and then say that how these initial conditions are achieved are not of concern. But then again, if we cut that out, we should also cut this out and say, okay, 2 volt came into action at t is equal to 0. In fact, when does it come into action? When did it come into action does not matter, because the initial conditions are given. So now the tricky thing here is VL at 0 minus is the inductor voltage, not capacitor voltage. So this being 2 volts may or may not mean that VL at 0 plus is also 2 volts. This is very important. However, knowing VC, we can for sure say this for VC, but not for IC as well. This is capacitor current, not inductor current. But we know this circuit configuration is in series. So this is also inductor current. Therefore, IC0 minus and IC0 plus are the same values, and they are 3 ampere. In this circuit, before t is equal to 0, VL was 0 minus. VL at 0 minus is 2 volts. and IC at 0 minus is 3 ampere. Okay, now I start making some sense why this UT is important. I will show you where what is the importance of having this UT now, and why writing that the system is assumed to be in steady state for t less than 0 is also important. So the system was in steady state, but this was given VL at 0 minus is 2 volts and IC at 0 minus is 3 ampere is also given. So at t is equal to 0 minus, the system would be a short here. The source is not still in action, and this resistor is there. The inductor is not shorted out, but the voltage across it is given. So at that time, we know there is a voltage in this polarity of 2 volt here. You see, we are dealing at t0 0 minus, and that VL is at 0 minus, that is given. And then this capacitor voltage, we do not know. There is a capacitor here, and the voltage across it is not given. We need to find that. But this current, the current is given, is 3 ampere for that instant. So the current in this is 3 ampere as well. And this is the circuit. So if a current of 3 ampere is flowing here, we will have a voltage drop of 12 volts here. So what will be, so if we write KVL, plus 12 plus 2 plus VC at 0 minus is 0. So VC at 0 minus should be minus 14 volts. This is the value of the capacitor voltage before t is equal to 0, and after t is 0 it will also be the same value because of the capacitor magic here of resisting sudden change in voltage. And inductor the voltage across the inductor after this voltage source has come into play is going to change. So the voltage across the inductor is suddenly going to change. Okay, let me draw that as well. So at t is equal to 0 plus, now remember these are instants of time. So when we replace a component by a voltage source, it is when we know the voltage at that time. So if we know there is an inductor behind this, but we also know this voltage. Or I could have drawn an inductor here without any issue with this voltage here. So we know this is this voltage. The KVL will still hold. So at t is equal to 0 plus, this source would have come into action as well of 2 volts. We have a resistance of 4 ohms and an inductor, the voltage across which VL at 0 plus is to be found, and we have a capacitor, and across this we have minus 14 volt in this polarity, and this current is still 3 ampere. Why? Because there is an inductor in the circuit, and inductor magic is going to keep this current of the same value. So still again this 3 ampere will make a voltage of 12 volt drop here, but now this will not be 2 volt. Why? Because here we did not have that 2 volt source, now there is. So write KVL for this case, minus 2 plus 12 plus VL at 0 plus and minus 14 is equal to 0. So we are going to get minus 14 minus 2 minus 16 plus 12 is minus 4. So we are going to get VL at 0 plus equal to plus 4 volts. You see the voltage across the inductor has suddenly changed because inductor does not say anything about the voltage change. It only resists sudden change in current. Similarly, this current may have suddenly changed for a capacitor, but because they are in series, this is not going to take place. So we have in a way handled all the initial conditions, and now after t is equal to 0, we need to find the expression for the capacitor voltage. Why? Because we want to find when will the capacitor voltage achieve 1 volt. So let us say the response that we are interested in is VC. So VCT is VC final value if this circuit keep operating forever, and we need to find the type of response, type of the nature of the circuit or the response. So this is a series circuit. Alpha is going to be equal to R over 2L. We are going to get 4 over 2 into 2, or alpha is 1 Napier per second. And omega 0 would be 1 over square root of LC, or 1 over 2 into 2, which is 1 over 2, which is 0.5 radian per second. For radian, actually we write rad. So alpha is greater than omega 0, which is a case of over-damped response. So now we can write here A1 e raised power S1 t. In fact, before writing this, find what is S1 and S2. So that is minus alpha plus minus alpha square minus omega naught square. We get minus 1 plus minus 1 square minus 0.5 square, and we get S12 equal to minus 1 plus minus square root of 0.75, whatever those values are in radian per second or per second, plus A2 e raised power S2t. So you would once again know what is S1, what is S2, but the question would be finding A1 and A2, and VC at infinity, if the circuit is remain in this position for a long time, then the capacitor will get fully charged equal to this voltage, so it will become 2 volts. So obviously taking a value of the voltage from minus 14 volts to, so at t is equal to 0 plus, taking the value from minus 14 volts, minus 14 to 2 volts is going to be, maybe because it's over damped, it may be something like this, maybe something like this, depending upon the circuit. May once overshoot but not overshoot again. And so in doing this, however, it is definitely going to pass from 1. The question is, what is this time? This time is to be found. So you should understand the question before knowing what to solve for. Then you make a strategy and solve it. So VC infinity is going to be 2 plus A1 e raised to power 1 of this value. Let me try to solve this for you. So 0.75, or square root of 0.75 is under root 3 by 2, or 0.866. So minus 1 plus minus 0.866 gives us a value of minus 1.866, and the other value is going to be minus 0.134, minus 0.134. So now we have minus 1.86. Does not matter which one is S1, which one you make S1, which one you take S2, does not matter. Stick to whatever you call A1 and S1 and whatever you call A2 and S2. Minus 0.134 t. So both are decaying exponents as expected. Okay, so this is the expression. Sorry, this is VC is equal to, the expression was for VCT. Now we need to find the constants A1 and A2. So VC at 0 plus, that we already know is minus 14, is equal to 2 plus, directly putting t is equal to 0, A1 plus A2. So 2 plus A1 plus A2 is equal to minus 14 is one equation. And taking the derivative and then putting t is equal to 0 plus, we know that dVc at 0 plus by dt is equal to derivative of a constant is 0, and again the derivative of this thing is going to give us minus 1.866 a1 minus 0.134 a2. I have put t equal to 0 as well, and we need to find this thing. Then we will get another equation, and then solving them simultaneously is going to give us a1 and a2. That's easy part. But what is this thing? So any expression that involves a dv by dt term, yes, there is c dv by dt, and that is going to give us this thing. So this implies that dvc by dt is equal to ic by c, and dvc at 0 plus is ic at 0 plus over c, and ic at 0 plus is il at 0 plus, and we already know is 3 over 2 is 1.5. So what do we get here? Minus 1.866 a1 minus 0.134 a2 is equal to 1.5 is the second equation. Solving both gives us a1 and a2, and then we can find the expression. A1 plus a2 is minus 16, and you can solve this. You can find this when once you write VCT is equal to 2 plus value of a1 found e raised power minus 1.866 t plus value of a2 found e raised power minus 0.134 t. Then for VCT equal to 1 volt, we can write 1 is equal to 2 plus again a1, the value you have found, plus a2. Now the question is solve for t. That value of t is the required answer. The question says when, how much time. So basically, if this whole thing started at t is equal to 0, then finding this value of t is going to give us this how much time, and finding this is going to be the answer desired, answer required.